All right, so now these two guys look like right here, the two different colors. So these are two charged particles. Okay, I can place it anywhere I like. So you can place one at the 0 and then other one maybe at 3 centimeter line right here. Exactly match it 3 centimeter midpoint of the particle. And I can change the charge particle number 1. Maybe we can add maximum possible negative value to that, negative 10 micron. And then charge particle 2 will set up into the maximum possible positive value. And then the force between them already shown here on the simulator. We will calculate that by using Coulomb's law and then try to compare to this one. Okay, that's the table number 1. It's a very simple calculation. You should know now how to do that calculation, but I will walk you through in a bit. Okay. And also you can click on the scientific notation that will allow you to see these large forces in scientific notation. That will be useful. That's all in table number 1. What we're going to do, we're going to take a look how that Coulomb force going to change as a function of radius. That means how far away these two charged particles. Let's bring these to maybe like 2 centimeter point. How many data points I need? 3, 3, 6, even 3 centimeter is fine. I think we can slowly bring it back each centimeter at a time. We're going to have enough distance to move. That's okay. We'll start at 3 centimeter. Okay. Any question? Radius should be measured in meters.
That's our lab for today.
Say it again.
That's our lab for today.
If you just join to the class, you have no idea how the class is run. Please stay after the class. I will explain you everything. Okay.
Okay.
Because we have 1 hour and 40 minutes. If I spend you like 15 minutes to give all the information, we're not going to have enough time. All right, so what we're going to do to understand the Coulomb law, we'll measure force actually, okay? Force measured directly from the simulator. Please change this into force measured, F measured. Force measured from the simulator, that's going to be unit Newton. And we'll calculate the force. This also, please change that into force calculated. That also unit in Newton. And PD, you know, we're going to do percentage difference between two numbers. There's no units. We'll use percentage sign on there, okay? All right, now I think you guys know what's the Coulomb's law and then how the Coulomb's law works, right? Coulomb's law is if I have two charged particles, there should be a force between them. That should be equal K, Q1, Q2 divided by R to the power 2, okay? Very simple concept. So if I know two charged particles, if I know the radius, K is a constant, what we call the Coulomb constant, 8.98 times 10 to the power 9. So if I know all of those, I can actually check this value, calculated value. The same number which is given in the simulator. So we can compare and understand whether the Coulomb's law behave as it is, because we know if I separate these charge particle more and more, which means the R goes to larger and larger values, force slowly goes to 0, right? So if R goes to the smaller and smaller values, force should be going to the higher number, which means charges are closer, forces should be higher, charges are far away, force should be lower, right? So that behavior we can take a look very quickly. It's going to take only 15 minutes or so to do. And you can get the idea if you click the charge particle red, positive one, and then bring it further away from the negative, you can see force value getting very much smaller, force vector getting almost very smaller as the charge particles separate out. If you bring it closer and closer, you can see force vector getting larger and larger, which means the Coulomb force is actually getting higher, okay? So that's the part we're going to take a look in table number 1. That's extremely simple calculation. So We'll start from the 3 centimeter point, but I need the unit meters, right? 0.03 unit meters. Force measured, the given value on the simulator, 9.99 10 to the 2. 9.99 times 10 to the power 2. You can just write this way, that's totally fine. But since these are large numbers, we would like to have Excel way of the scientific notation. So you can change this into scientific notation, the number which I write here. If you put an equal sign in front, that will automatically change into a scientific notation. Put the equal sign in front, then highlight all this column. Then in the middle part right here, last time we talked about it, all of these things, how to work with the Excel, change this into scientific, and then it will show the scientific notation, how the Excel identified 9.99 plus 0.2. So the Excel doesn't identify 10 to the, it can actually identify 10 to the power 2, but Excel shows in writing the scientific notation with the letter E, okay? So that's a better way to use when we use in the Excel. Any question? Okay, and that's all really. Then we'll calculate the force between the charges by using Coulomb law, equal sign, charge, the constant 8.98 times 10 to the power 9 positive, and then multiply by the two charge values. Both charges are 10 micron, which means 10 times 10 to the power negative 6, multiply by another 10 times 10 to the power negative 6, divide by radius to the power 2. So that will KQQ over R squared. Let me take a look why it's giving me 10 to the wrong power. Let us take a look why that. Number is fine, you can see it's good, 9.99, 9.97, but the 10 to the power value is actually not correct. Let's take a look why. Micron 10, that's good. Let me check what went wrong there. Okay, so I think maybe this one. Let's put parentheses on there. Still 10 to the power is not correct. Let us take a look that very quickly. Okay, I found it right here. I have extra, I think, power. This should be 10 times 10 to the power negative 6. Okay, now it's good. And also change this whole cell into scientific. I will copy paste all the commands. Okay, then you can check that. So both of them should be exactly the same, but you can see slight different in like second decimal place. Reason is one is recalculating. Okay, let me copy paste that function. So that's the command we're using now. I'm gonna place it somewhere here. Okay, that should be our if calculated. Okay, force calculated. Okay, so which means the Coulomb law is actually nicely working out, but there's a slight difference. Because of that, we'll do the percentage error, right, to compare those two numbers. ABS, open brackets, expected value, that is the measured value minus calculated value, divide by open double brackets, measured value plus calculated value, close brackets, divide by 2, close brackets again, multiply by 100. So make sure your percentage error just a number in decimals, not the scientific notation, because we would like to see that as a percent number, whether that's a large or small, because if it is larger, our calculated value going to be very incorrect. If it is small like this one, which means our calculated value is very correct. Okay, so that's the idea. So let us copy paste that command also. That's the PD. Any question?
Sorry, Professor, what is the F measured?
F measured is a number given here. You see that? Force
Oh,
on the
okay.
Q2. Yeah, that's we read indirectly.
All right, got it.
Yeah, yeah. That's all. It's a very simple calculation, very simple way to check whether the Coulomb law is actually working as it's saying, or there's something different. Okay.
So
Now,
the information that we put in the table is from the Q2 each time.
you have a question?
Yes, the information that we put in the table is from Q2. Like we put the difference from Q2 to Q1 each time.
Exactly. Yeah. This R is that. Exactly. Yeah. Yeah.
Okay.
Yeah. R is the separation between the charges. Now you can see the simulator showing the charge like really big. Because of that, we measuring center to center. Okay. And now
How
to
did you find the
really,
percent error?
you have another question?
Yes, how did you find the percent error?
That's right here, the command.
These
see
commands
that?
we have to type in, or we have them as given?
You have to do all this function in the Excel file. Okay, now to understand how the force is, Coulomb force is changing as a function of radius, I have to actually change the radius and then see that calculation, right? We expecting force to be lower. So let's change this one, right? Just click this positive charge, and then let's move into 4 centimeter location. Then my distances now going to be 0.04 because 4 centimeter divided by 100 going to be the unit meters. And the force measured is 5.91 times 10 to the 2, 591. If you type 591, it will automatically change into a right scientific notation, but make sure you change this column, these 2 columns into scientific notation by using right here in the middle. And the last column, make sure that is in normal number notation because that's a percentage error. Okay. Now it's in the simulator, it's fine, it's decreasing, right? That's what we're expecting because it's inverse proportional. But let's take a look whether the calculation does the same. In Excel, you know, if we do one calculation, we don't need to repeat it again. You click on the cell, right-hand side, very bottom corner on the cell, you will see green color, small dot. Click on that dot and drag downward. You can see 2 numbers are extremely close. This number is slightly different. That because that's our calculated value. So let's take a look. The percentage error also same way. It's about 5%. Question.
I still don't get how you calculated the percent error.
You are the one who joined today's class. You were in the last time in this class?
No.
Yeah, if you never in the class, you don't know how the class is running, okay? These are the commands. You have to use that command to do this calculation with the Excel file. Excel file is already given in the Blackboard, okay? Blackboard has all the information. You go into the last class, week number one class, take a look the video, then you can learn, okay? If you miss a class, please take a look. Everything is there. The whole 2-hour session is recorded. That recording has every single step what you are doing in this class, okay? So the only thing I can say is that this will be difficult all of a sudden for you. You can probably stay after the class. I can give you some information, okay? All right, any other question?
Wait, can you just show how you got the F calculated for the second row again?
Oh, that's only thing you have to do now. We done this cell earlier, right? Calculated value. So since we done that calculated value, you have to go back and click on that cell.
Yeah.
Then around the cell, you see that green color line. Right-hand side, bottom corner, you see the green color small dot, solid dot. Bring the cursor on top of that,
Yeah.
then click and then drag downward.
Got it. Did it. Okay. And can I see your FM cell? Just I want to see the formula in that FM cell.
FM, there's no formula. This we directly reading from here, from the
Okay.
simulator,
I'm
this
sorry.
number.
Here's the thing. Where'd you get the simulation from? Because I'm trying. Because I
Oh,
clicked on.
yeah, this simulator is actually not on the lab manual. I put it that onto the chat box. Let me put that again.
Yeah, I was just confused because I'm like, how are we supposed to do this on our own if like are we supposed to copy your numbers?
No, you have to do it yourself. The simulator link on the chat box. I put it now twice.
Okay, it's in the it's in the chat box. Oh, I'm sorry.
Yeah, just click on that, then it
Chat
will
box.
open up.
Got it,
Yeah.
got it. I was looking in the notes. There's a different in the lab, like
Yeah, this part is extra actually.
okay, perfect, got it.
Yeah.
Okay.
All right, now it looks fine, right? It's decreasing. So that's all really. We just observing that by using the simulator. So all we can do, we can maybe do a couple of more data points to see that behavior, right? So let's increase this separation into maybe 5 centimeters and then read the force from the simulator right here on the top. And the separation 0.05. Force is about 374. Make sure that's written in scientific notation. These cells you can even click and drag together. It will do the calculation automatically. Okay, it's fairly consistent. And then that's it. We'll do another 3 more data points for that. It's not big deal. It's the same thing. We just increase in the radius between the charges and then repeating the calculation. This is now 258. And sorry, the separation is about 0.06, about 6 centimeters, and then the measured is 258. Calculated, you can click and drag. If you do once the calculation in our Excel file, then we don't need to do it again and again, same column. So you can click and drag, the rest will automatically do it for you. And we'll do 2 more data points. Next one.
Professor.
Yeah, what's up?
So I'm like doing the exact same thing as you with the simulation. Can
Mhm.
I like is it okay if I have the same numbers since I'm basically just following along with what you're doing?
Oh, yeah, that's okay.
Okay, thank you.
Yeah.
Professor.
Yeah.
I'm sorry, for the charges, do you want us to stay with the -10 and the +10, or do you want us to come up with our own charges also?
You can actually use any other number if you like, that's okay, but I try to keep these maximum values, positive and negative.
Okay.
Even it's a positive, you're going to get the same number if it is a 10 and 10, doesn't matter actually, only the force vector direction changes. We'll do 1 more data point, say 8 centimeter maybe, 144. So it's fairly consistent, the error values and everything. So any small difference here in our radius, it should be exactly matched with this number. If I have a slightly off from there, so my measured value going to be slightly off. That's why we have a little bit of error here. So what we really like to observe is the behavior, right? How the calculated value is decreasing as a function of radius increase. That's what exactly we observing. Okay, so that what we like to see. That's the behavior of the Coulomb's law. This part is extra. This is not really what we're trying to do in this lab today. We would like to do how the electric field behave. Okay, that's the real lab. Let's start that one. Any question? Everybody able to do this part?
Yes.
Okay, so Then let's go to the lab manual. And then lab manual, we have another link right here on page number 4, PHET Colorado link. Just click on that. That is the link actually what we need for today's lab, okay? That should be like black color background, and then there are some function to the right, and then there are a few items on the bottom, and then there should be a yellow line, that's a reset button, okay? And now what we're trying to do in this lab, this part, now the Coulomb law, I think you get an idea how it should be calculated and so on. So the idea now, we would like to take a look how the electric field behave. We know if I have a positive charge, electric field is actually electrostatic force divided by the amount of charge at any given point, right? So which means if I have electrostatic charge particle right here, electric field by definition should goes away from that charge. If I have a negative charge particle, by definition, electric field should be goes towards that charge particle, okay? Now, the main idea of this lab is we try to understand how this electric field line behave if I have a different shape of charge particle. Like if I have a just two charge particle like this, what this electric field map look like? Starting from positive should goes to negative, right? So always starting from positive should goes to negative. So it should look like this kind of behavior. That's actually one important thing we try to accomplish in this lab. This actually called the field map, electric field map. Now, if we're doing this in-person setting, these electric field lines are invisible. We can't really see that electric field. Because of that, what we generally do, we actually try to understand the electric field by measuring the electric potential. That actually the planned general method if we doing this in-person setting. Electric field is equal changing potential or potential different divided by the distance between them. If I have two electric potential points somewhere in the electric field. So by using this concept, if you're doing this in-person class, because the potentials we can measure directly by using multimeter, distance I can measure directly by using the meter ruler. So I can actually calculate the electric field around the charge particle because that field lines are invisible. But the simulator will show you them, okay, directly. So but in the simulator, since the electric field is directly visible, we're not gonna calculate electric field by using, we can do actually either way. We can measure the potential, then by knowing the distance, we can actually calculate the electric field. And also in the simulator, there's a sensor, we can measure electric field directly. So we can go vice versa, okay? But we'll do this way, the same way like we do in-person setting. So we'll set it up a charge particle. And then we'll go a little bit further away, R distance away, pick any point, and then measure voltage on there. And then if you go around this the R distance away from the charge particle, by searching this exact potential number, we'll say this number is like some value, let's say maybe 10.5, okay, volt. If I go around and then search the same voltage V1 around this charge particle, then you can connect these dots at the end. That connection, this dotted line goes around the charge particle is actually called the equipotential line. Equipotential means you go around a certain electrode. If you have the same voltage everywhere, that line is actually the equipotential, okay? So this blue line right here is the equipotential. If I have a point particle, equipotential should be a certain. That's the idea, okay? So if we do in-person setting, what we're going to do, electric field is invisible. We're going to measure few different points, potential values like V1, V2, V3, V4, and then so on. Then we're going to find the potential difference here. We know the separation, take the ratio, we can calculate the electric field. That's the general way we do in-person setting, but the simulator is much easier. That's going to show everything. We can even measure electric field values and all the information directly, okay? Any question? All right, so that's the plan. So in our table number 2, we'll set up electrode, like the point-like electrode. And then by using that point-like electrode, the potential around the point-like electrode, we'll try to calculate electric field. That's the plan. By calculating electric field, we can do one other thing. Because if I have a point-like electrode like here, if I calculate the electric field exactly this location, you know electric field around the charge particle should be kq over r to the power 2. From this equation, by knowing E and R and K, I can actually calculate the Q. Q gonna be E times R to the power 2 divided by K. That calculation is useful because in the simulator, value of the charge value right here, it's given. We know what's the amount of charge particle we are using. If you do that calculation, by knowing the Q from the simulator, we can actually compare these two, Q known and Q calculated. If I have the same answer there, then we know all of these concepts are actually valid, okay? All of these concepts are valid. That's what we're trying to do in this lab, okay? Validating all of those concepts by simply measuring the voltage around the charge particle. That's the plan. Any question? Okay, then let's go to the simulator and then right side, you will see different options in here. You can click the values and the grid. You can then see the graph sheet, okay? And then below that, you will you can see the graph sheet is not really visible because of the black background, but I can change that color. If you bring the cursor on top of this PHET letters and then do one click, then you will see an option icon here. Then click on that. Then you will see the projector mode. Just click on that. If you click the projector mode, that black color change now into the white yellowish color, then I can clearly see that graph sheet, because that graph sheet is important because our plan is to measure the voltage in different location around the charge particle, okay? All right, so any question? And now what we need to do, bring a charge particle. Let's bring a positive 1 nanocoulomb and then place it anywhere here, exactly in the middle. As soon as you place there, you see the red arrows. That red arrows are actually electric field lines. Now the problem with the real class, you can't actually really see those red arrows, right? Those are invisible. And the charge particle also, we can't do this way. We have to have a battery and the electrode, right? If you're doing this in-person setting, we're going to create the charge particle. We have a battery somewhere, and then by bringing the wires, and then we're going to connect that into a like copper metal plate or metal dot, then actually you can create, this is a positive charge particle, and then this is like a grounded place. Then in between right here, we will see the electric field lines, okay? All right, guys, any question? Anybody have any question? If you don't have any question, please mute yourself, okay? We hear a little bit of background noise. Okay, I think should be good. All right. So now we have a charge particle. We now see the electric field lines around it. So in-person setting, which I talking earlier, I need to have external battery to actually create this, but in the simulator, we don't need to worry about any of those. Now let's, in terms of measuring, now what we like to measure the electric field values, there's electric field sensor here, right? So we can actually bring that and then directly measure if I want electric field anywhere around this charge particle, but that is not our plan. Our plan is to measure the voltage around it and then calculate the electric field, okay? That's the plan. On your right-hand side, you see that blue color box. So that is a voltage sensor. If you bring that anywhere, you can see it will actually give you the voltage value at any given point. Okay. Now, if you zoom in this picture, you can see that each small square values. So it's I can easily measure voltage by moving, starting from the charge particle, moving maybe one small square values at a time. Okay. And the value of one of these small square on our graph paper, to understand that, you can bring this small icon, yellow color, that is a tape measurement. If you bring that, you can see this larger two lines, in between large two lines, larger square length is about like 50 centimeters. 50 centimeter divided by 5 small squares. So which means each of the small square right here is about 10 centimeters. Okay. Which means we don't need to measure every time. We know that a small square is 10 centimeters. Okay. Which means I can slowly move my equipotential or the potentiometer around the charge particle, starting from somewhere here, and then slowly move away and then figure out the potential. I need few potential values, and then we can calculate the electric field by knowing the potential. Okay, that's the plan. Any question? Okay, so that's extremely simple calculation. So you know now what we're measuring will start from. We can take a nice screenshot also, this one, because the later at some point we're going to be, maybe next week or so, we'll do our first lab report. Not every lab needed the lab report. Okay, we're going to do only 4 lab report. I will tell you which lab needed to do the lab report. Okay, otherwise it's just the data table. So if you're doing the lab report, all of the simulator picture you have to collect. So to practice that, we'll collect one of those simulator here. Simulator picture here, there's easy way to bring that here. If you click on the insert and then go into the illustration or pictures, then you will see a screenshot. Click on that. Then you will see different options, and then there's option should call screen clipping. On that, then I can take a screenshot anywhere in my screen by selecting exact area. Okay, I'm going to take a screenshot showing nice nice picture of our simulator, which has the one electrode, positive electrode, and then I have my tape measure to get an idea about how the length is, and the voltage measurement. Okay. If you have any picture, make sure picture has to name. All the table names go top of the table. Usually picture names go below the picture. Okay. So the picture usually name as a figure. This should be then now figure 1. We can say this is an electric field simulator, right? Electric field simulator for point electrode. Okay. So make sure if we have a picture, always it has to name properly by using figure term. Okay, so that is actually needed if you're doing the lab report later. This should be included into your lab report. Okay. All right, now let's continue.
Professor, sorry. Can you show me how to insert the picture again?
Yeah,
How do you do
that's, yeah. There's a lot of different way, but this is one method. Okay, this method is a little bit easier. You click on anywhere on the Excel page and then click on the insert very top. And then you should see, let me expand this one a little bit. Then you should see this area if the Excel is on the whole screen, where it says illustration, and then you should see a screenshot. Just click on that. Then or inside there, you should see screen clipping. Then click on that. Then it will allow you to actually highlight the area you need to get the picture. Okay.
All right.
Then
Thank you
click
so
and
much.
highlight. That should automatically come into your Excel page.
Thank you.
Yep. All right. So let's do this measurement then. Yeah, the simulator, you can zoom in. How I zoom in, if you put your left finger and right finger on the touchpad on your computer, then place this closer in the middle and then take it away from each other, 2 fingers on the touchpad. Then this picture automatically zoom in. If you put the fingers far away on the touchpad, bring it closer, then it will actually zoom out. Okay. I think it should work in any computer touchpad in generally. Okay, good. All right. So then let's continue. Now let's measure this one, right? Voltage, what we need, the voltage and the separation. Let's measure each 10 centimeters. Make sure this charge particle midpoint somewhere exactly with this crossing point. Then we know I am measuring my length relative to that exactly midpoint of the charge particle, okay? Right here, and then start measuring each 10 centimeters. 85.78 potential in unit volt. Radius, I need unit meters. Electric field for point electrode gonna be then volt per meter, right? And we'll calculate the charge, should be Coulomb. Then we'll do the percentage error because we know charge calculated should be equal to the charge we already have in the simulator. That is about 1 nanocoulomb. All right, so the potential after 10 centimeter, 85.78. And the radius is about 10 centimeters, which means 0.1 in meters. I can have 2 decimal place in our radius. The reason the smallest value of this graph paper is about like 5 centimeters. Because of that, you can add 1 more decimal place to radius. Okay, that addition or putting more decimal places or taking off, you can do right here on the top home menu bar. Right here in the middle, you will see a number. Then you will see right or left arrow. By clicking them, I can add or get rid of extra decimal places. Okay, that just to show the accuracy, because in the simulator graph paper, I can actually measure to the 5 centimeter point, half the 10 centimeter lines. Okay, and then let's do electric field, volt per radius, and then let's take a look the charge value. Let's calculate that too. Equal sign K 8.98 times 10 to the power positive 9 multiplied by r to the power 2. R is this cell value C21 power 2 divide by so let's take a look. This one, everybody okay? I copy paste that also. Right here, let's do that command right somewhere here. That's going to be electric field calculated. And then by knowing electric field is equal KQ over R to the power 2, I can calculate the charge, okay? So then charge going to be electric field times R to the power 2 divided by K actually. Electric field times R to the power 2 divided by K parentheses 8.98 times 10 to the power positive 9. And close brackets. 9.5 times 10 to the 10. I am expecting 1 times 10 to the 9. So it very close, the value we expecting, right? So that's a good number. So that's what we're checking really. That can confirm everything. The Coulomb's law is valid. Potential rate of change of potential is electric field, that is valid. And by just calculating backward to the charge value which we actually have in our simulator, okay? The number we expecting, I will write it down on the top here on this table, because that is our reference value, right? So the value we're expecting for the charge in this case, 1.0 times 10 to the power minus 9 coulomb. We are getting about like 9.5 times 10 to the negative 10. That means about like 0.9 times 10 to the negative 9. 0.95 times 10 to the negative 9. It's very close. Let me copy paste that command also. You can't see the command earlier, right? Okay. So let me copy paste that function on here. That's going to be then Q calculated. Okay. I think you can see that now, both the command, both the function which we're using on just right hand side bottom corner here. Okay. Okay, question. Let's do the percentage error to equal sign ABS, open brackets, charge expected 1.0 times 1.0 times 10 to the power minus 9 minus calculated E21 divide by open brackets twice, open brackets, expected value 1.0 times 10 to the power minus 9, close brackets, multiplied by 100. It's about 4% error. Question. We copy paste the percentage error command also here. All right, any question?
Professor, where are you getting the expected charge? The 10 times 10 to the negative 9?
It's not 10 times, 1.0 times 10 to the negative 9.
Yes, that.
Because this charge particle right here, what we're using, is actually 1 nanocoulomb. Nano is 10 to the negative 9. That's
Okay.
why. Yeah.
Okay. So if we raise that though, it would change. If we change the charge particle, it would change, right?
No, this simulator has every charge particle you're bringing has the same value. 1 nanocoulomb.
Okay, so
not
we can't change it. Okay, all right.
Yeah, I think we can't change that. We can add more charge particle together to get, larger number, but if you have one, that should be 1 nanocoulomb.
Okay.
Yeah.
Wait, Professor.
Yeah.
How do you do the charge calculated formula? What is it?
Oh, that's right here. Can you see that?
Yeah.
Right here.
Wait, the Q?
Yeah, QCal. That should be equal sign and then everything.
Where'd you
after.
get 8.98 times 10 to the 9?
That's K.
Oh, that's just a constant?
Yeah, that's a Coulomb constant right here, which we wrote earlier in the Coulomb law. This is Coulomb constant. That is about that number, 8.98 times 10 to the positive 9.
Okay.
Yeah.
Okay, thank you.
Yeah, then all we're going to do now is just change the position of the potentiometer, potential sensor, and then we'll get that position a little bit away from the charge particle. Now it is at 10 centimeter location. We'll go 20, 30, 40, 50, and then so on. Let's redo this calculation and then estimate the charge value again to see whether we get in the right number, our expected value. If we get in the right number within a considerable error limit, then we are fine. Okay. The errors happening, the one reason why the errors happening, you can see, I want to put this, that cross sign, that exactly 10 centimeter point, but the error of this graph sheet itself about 5 centimeters, right? Uncertainty is 5 centimeters. So smallest change which I have there, going to be huge error. That's the problem. So we thinking that we placing exactly at 10 centimeter location, but it may be just 9.5, maybe 9, maybe 10.5. It's difficult to find out that, okay? That's why one of the reason why we see the error. Okay, then let's move this one to 20 and then we'll repeat the same calculation. 20 is next is smaller line, okay? That's going to be 4476. 4476. 20 means 0.2, right? In meters. And then these values you can actually calculate. You can click and drag all of them. Then it will do the calculation. Now, next one, you can see the error is much lower, about 0.3%. So because my position value may be very accurate there than the previous. That's why, okay. The smallest change on that crossing point in between that line exactly I want to place, going to create actually huge error than we think, because that r to the power 2 in meters, so that create a lot of error there. Okay. All
Wait,
right.
Professor,
Yeah.
could you
Yeah.
show the percent error formula? I
Oh,
can't.
sure. Yeah. I think we can make it smaller, then you should be able to see that. Let me check that. Yeah. Can you see it now? Good.
Yeah, kind of. That's
It's
one
too
times 10,
small.
that's 1 times 10 to the 9 times e to the minus 21.
No, it's not time. It actually minus sign there. Okay. Let me zoom in that one. This one. Equal sign ABS, open brackets, 1 times 10 to the power minus 9 minus E21. That is the cell value, close brackets. Divide by 1 times 10 to the minus 9 times 100.
Let me just see if it's exactly the same. Okay.
Okay, got it.
All right. Thank you.
All right. Anyone else? Any question? Then let's continue. The rest is just we repeating the same with different potential values. We done now 20 centimeter location. Let's do this 30 centimeter location, right? 30 centimeter, 29.40, 29.40, 0.3 centimeters. And then these cells we done once. That's the advantage using Excel. After you done it once, you can just click and drag. Even you can see I can click and drag all of those three together. Highlight all of these three together. Go to the very right hand side, that solid green dot, and then drag to the next one. It will do the calculation automatically for you.
Oh, Professor, one more question. Did you
Yeah.
want us to put our name on the picture somehow?
Name means the picture need to rename right here as a figure 1.
Okay. Okay. That's it. We just have to leave it here and that's it.
Yeah. So your name should go here. Okay.
Okay. Yeah.
On the top. Yeah.
Thank you.
And let's.
Screenshot, right?
Right. Yeah. Right now you need only one, but we may need 2 other screenshot for the next table.
Got it.
Okay. Yeah. That's it. Then we'll continue this to the next line, which is 40 centimeters, right? 10, 20, 30, 40 away from the positive charge, 22.88, 22.88, 0.4. And all of these I can click and drag. That's the advantage. You can see if you're doing with the calculator, you have to do each of these calculation again and again, right? But I don't need to do that now because Excel is actually automatically do the rest. I just need to take care of the very first data point. That's it. If I know everything correct there, the rest is extremely simple. All right, then let's continue to the next point. We'll take another 2 points. Then we'll go to the next table. Okay. Next point is about 18.06. And it should be about 0.5 away. Still our error is very low. You can do one other thing. Probably you can see there's too many decimal places show up here. Both of these, right? I don't need that many decimal places. Probably you should change decimal places to maybe like 2 maximum, or maybe 3. Since it is calculated values, it's okay to have a little bit more than what's a significant figure required, but don't need to have very, very large amount there. Okay, that not make any sense. Just do maybe 2 decimal places into 3 sig figs, all of these numbers. And the all of the percentage error, you can do maybe similar. 2 decimal places. And right here, the electric field calculated values, also you can keep 2 decimal places, okay? So all of these, you know how to reformat, highlight that column, that cell area, go to the top middle part on the menu bar, says the number, then just click the right or left arrow. There's a 2 small right or left arrow, green, blue color. By clicking that, you can just easily change the number of significant figures needed, okay? Okay, now it looks fine. Then let's do one other last data point for that particular case, 15.14. And then this is now about 60 centimeters away from that. So then click and drag, it will do the calculation automatically. Okay, any question? Make sure all the units are done correctly. Make sure all this reformatting, we done a little bit of reformatting, right, into significant figure. This particular part right here, scientific notation, because that's extremely important there. That's a small number. So all of those are good. Then we done with the table 2. We can continue to table 3 if you don't have any question. Anybody have any question? Need any help? Okay, then let's, anybody have any question?
Yeah, Professor. I
What's up?
put the formula in for the percent error,
Uh-huh.
but I'm getting like some really big numbers.
There should be something wrong.
Yeah, I did
Can you check
absolute
again
value.
with this one?
Yeah, absolute value, parentheses 1 times 10 to the minus 9.
10 to the power, you have the power correctly?
Oh wait, for some reason, I'm actually looking at the formula now. Like the formula, like the Excel formula made it e to the 22, then e to the 23 with every next like row. For some
Oh,
reason.
that means something wrong probably. So you may need to take a look again. Exact formula look like this, that hat and everything should be there. If something wrong, then it will give you very wrong answer. Okay. If very difficult to figure out, you can wait after we finish. I can take a look. Okay. It should be simple thing. Just need to do a little bit of adjustment to the equation. I think probably should not be a big deal at all. Any other question? All right, then let's continue to table number 3. That's our last table. So that table, we're not going to do charge estimation because we can't do the charge estimation. The next table, what we're trying to do, different shape of electrode. If you, in the class, I think you probably have done this part now. If you have a different shape of the electrode, for example, let's say I have electrode look like a plate-like. Just this one, okay. Let's say if I have electrode look like a plate-like, then we call generally the line charge, right? So if you have electrode look like that, everywhere is positive, that look like a line charge, one-dimensional. Then you go r distance away, and then right here it should have electric field, but earlier version of the equation I can't use because this is very difficult depending on the geometry. You have to use the integral to calculate that, have to figure out a small charge particle q here, then figure out what is the electric field due to that, then you have to integrate. Because of that, the formula right here is not exactly the earlier equation. I can't use that simple charge particle formula to do the electric field analysis. Because of that, we're not gonna do that charge particle calculation. Okay. However, still electric field, I can do that other way around. Electric field should be rate of change of potential. That is still valid. If I know the potential somewhere right here, and then if I know the separation, then by taking the ratio or the ratio between the potential and the displacement, still I can estimate the electric field, but the charge I cannot, okay? Because that formula is very different than the previous one. Because of that, the next table, we're not going to do charge analysis. Just we're going to take a look basically whether the electric field changes if I goes away from the line charge or not. That's the idea, okay? So let's do the plate-like electrode for this case. So to do the plate-like electrodes, what we have to do now, you can see plate-like electrode is not given in our simulator, right? Let me zoom out this one. Simulator look like this, right? I can have only one particle, but I can create the plate by doing this. I can put one particle here and then bring more particles and then put it close by each other. See that? If I put it close by each other, particle after particle, then technically I can build a rod, right? So that look like now charge rod. So that's what you have to do. Doesn't matter how many charge particle you bring, maybe like 10 or so, that should be good enough. Probably 4, 8, 9, we'll do one more, 10 charge particle, okay? So now that look like a rod, different shape, right? That's the plate-like electrode we generally call. If I have a plate-like electrode, let's take a look how the electric field look like if I have a negative side on the other side. But the same plate-like electrode, okay? So let's put the negative charge particle other side, and then let's take a look how the plate electrode look like. You can see all the electric field line must start from the positive by definition, and that should end at negative because electric field we define per positive charge particle, okay? You can see it nicely starting from the positive electrode and all the arrows goes to the negative. And in the corners, you can see it's bending, right? Other side, it has to come somewhere. It bend a larger bend and then it should end up at the negative side, okay? Same concept. Now, in this case, we're not going to do charge estimation at all. What we're going to do, just simply going to take a look if I bring the sensor away from the electrode, we can do either side. If I bring the sensor away from the electrode, whether electric field is decreasing as a function of R or not. That's what we're expecting. It must decrease. That's what we try to understand, okay? You can easily see actually if you click on this voltage icon right here, right-hand side very top, that is how the voltage variation, blue color side is the negative, red color side is a positive background. Then in the middle, you can see like white color, like the vertical line. So there, voltage must be 0. If you bring the voltage sensor, you can see it very close to 0 there. Somewhere I can identify exact 0 point in the middle of that. That's the idea, because I have positive side and negative side. In between, there should be a 0 point, okay? Any question?
Why the voltage would be 0 in between the positive and the negative?
Why it is 0 in between positive and negative?
Yes.
Because if you bring the positive, if you bring the sensor right here, you can identify that. Now you can see if I bring the sensor right here, it has huge electric field. And then if you bring very closer to the negative side, electric field actually change the direction, right? So technically, this is what we generally do. This is in-person setting class. Let me go there, then you will get a better idea. If this is in-person setting class, what we do, there's no negative side actually. What we have is the battery negative terminal. Battery negative terminal is technically the 0 potential. But in this case, the problem is, now this side is the voltage 0, this side is the voltage positive. Now in your case, now in our simulator, this part is actually not there because we putting charge particle ourselves, positive charge particle in one side, negative charge particle in other side. So the potential 0 point somewhere should be in between. The potential is actually what? Potential is generally potential energy per unit charge particle. So what it tells you, if I have a charge particle, if you want to bring charge particle, another charge particle from outside to this place, then you have to do certain amount of work, right? That amount of work for positive is actually positive work done. For negative charge particle, it's negative work done. There are going to be some place where if you add these two together, you will get 0. That's why exactly in between, you're going to get 0 point. Make sense? Any
Yes.
question? That's why exactly that midpoint becomes actually 0, okay? But we can't really do that in experiment situation. Experiment situation, 0 is actually our negative terminal. It is a grounded one. But that we can't do actually with here. With the simulator, we can't do, there's no any grounded one, okay? All right, now let's take a look. Any other question? Okay, then let's take a look what we have here. All right, now what we're trying to do in this case, we're just going to measure a couple of voltage values. You can do either, doesn't matter. You can do if you want to negative side, positive side, or maybe other side of the positive electrode, in between the positive and 0, doesn't matter where we do. We're going to basically do a little bit of calculation to see electric field value. It should be constantly decreasing when we go towards a zero direction, okay? So let's take a look whether that's happening here. So I can zoom in this little bit, and then we can start measuring somewhere in middle of the electrode, starting from this point, okay? That's about 10 centimeters from my electrode towards to the 0 side. And then if you slowly bringing this side, you can see it actually decreasing number, right? See that? Decreasing, 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 and becomes 0 somewhere here, and then goes to the negative side. So that's all really, it's a simple measurement. And one other thing before we start measuring, we need actually screenshot of this one too, right? So it's our electric field map. So let's take a picture of that one and then put it into somewhere maybe here. Okay, I think this place is better. Insert illustration, screenshot, screen clipping, and you can take a picture with nicely our electrodes and also potentiometer maybe. No need to have this much bigger. Okay, make sure it's get a little bit smaller. Maybe that size is better. That's good enough, I think. And also make sure you rename that, okay? This should rename as a figure. This should be then our figure 2. You can say this is plate-like electric field map. Electric field map of plate-like electrode. Plate-like electrodes, okay? Any question?
No?
Any question? Okay, then let's continue. All right, so the potential we're going to measure again, V radius, R in unit meters, right? And the electric field, you know, rate of change of potential, that should be V per meters, okay? Volt per meter. It's same 3 unit for the other one too, this side too, because that side what we're going to do, we're going to take a look by changing the electrodes, one of them to like point light, and then one of them keeping as a plate light. We're going to take a look how the electric field look like, okay? That's the plan. So let's do a little bit of measurement there.
Professor, what would you title the other picture?
Say it again, how?
Oh, I said electric field map of plate-like electrode.
Oh, the name, I just name it like electric field map of plate-like electrode, okay? All right, then we'll do voltage measurement. You can zoom in the picture, that easy to measure then. Away 10 centimeters away, 249.2, 249.2, 10 centimeters away. Maybe I should keep 1 decimal place extra, right? For the radius and the electric field is actually ratio between them. And let's check the electric field as we go away from the electrode 20 centimeters away, about 179.8. And this radius is now 20.2 electric field. You can click and drag, okay? You can see it decreasing rapidly still, okay? Even it's a plate like, now I can't use that point like formula to actually do any calculation because the formula is very different, but still you can get an idea, it actually decreasing very rapidly, okay? Exponentially it's decaying. And maybe now 10, 20, 30 centimeters, 0.3. The value is about 141.1. And electric field, I can click and drag, 470. If there's a lot of decimal places, always make sure you get rid of them. We don't need that many decimal places. Yeah. We have fairly large numbers here, maybe 1 decimal place, or maybe you can convert if it is a much larger number into scientific notation. That always better. Okay. Let's do two more values. Next one, maybe 40 centimeters, 113.6. 113.6, and the electric field is now 284. You can see it started at 2,400. Now it's almost 280. So that's the only thing we can actually directly measure and calculate. We cannot estimate the charge directly at this case. Okay. Then the next one is 90.75. Then the radius is now 0.5. Electric field is almost 181. Okay. Any question? If I go much further away, always towards that white color, you can see electric field value is extremely smaller. If I divide by distance, electric field going to be almost very close to 0 there too. Okay, any question? All right, then let's take a look. Then let's take a look the next shape of the electrode, which means I need to have one plate like and then one point like, okay? So to get that, we can maybe get rid of some negative charges on this side and then keep only one here. Then I can have positive side look like plate like and the negative side look like point like, right? Now, if you take a look the field map, if you get rid of that voltage, then you can see nicely the field map right here. You can see how the field map now look like. All the lines starting from positive should be going towards the negative, right? So around negative side, it's become more curvature. Close to the plate, it becomes more linear, horizontal, because around the plate, it should be 90 degrees to the plate, all electric field lines, okay? Any question? Okay, now let's take a look how the potential varies. Now, potential line going to be always perpendicular to the field lines too, right? So I forgot to mention that earlier. Now, if I have a positive charge particle here, negative here, electric field line goes from positive to negative. If I have an electric potential point somewhere here, V1, if I go around the charge particle, potential line going to be look like this dotted line. Around here, potential going to be curved other side. In the middle, you remember that white color space there. In the middle, you will see potential line almost linear. Okay. Now, same for this one. I have now positive electrode look like this, and the negative only one charge particle. Everything is starting from positive should go there. So that's the field map. Field map you can see directly there. Now the potential map going to be the look like this dotted line. All the equipotential line close to the plate should be look like linear, but when you go towards the point particle, it should become curvature. If you do in-person setting, we're going to draw this line first, equipotential lines, and then we're going to draw the electric field lines because electric field lines are invisible. Okay, that's the only disadvantage. Doing with the simulator, you can directly see that. We don't need the electric potential line at all. Okay, any question? All right, so that's let me take a look what are the shape it asking, two plate like, and then we can do maybe, yeah, that should be good enough, I think. One other thing actually I forgot earlier, so we can actually visualize this electric potential lines too. Let me show you that too. By duplicating, if I bring one charge particle here, potential line, probably I can draw this way too. Any other questions so far?
So what data sets do we put in the point and plate electrodes table?
We're going to do it right now. The data
Go
for
ahead.
this one, right?
Oh,
Yeah,
Yeah,
we will
go
do it
ahead.
right now. Yeah.
Sorry.
Okay, guys. So what I was telling you earlier now, you can see in class, we actually going to draw this electric potential line first, and then we're going to draw the electric field lines, right? So we can't actually really do that here because electric field lines directly visible is still, if I want to actually draw that, I can use this potentiometer right here and then figure out where the exact potential is. Now, this is one place where the potential is about like 0.2. If you click the pencil, you can see I can actually generate the electric potential lines, right? That's what actually we do in person setting. We're going to first draw that. Then on top of that, we're going to draw electric field lines, okay? That's how we're going to generate the map. But we don't need that line right here because the simulator going to tell you where the electric field lines are. That's the advantage using this one. But in class setting, to get this one green circle, you have to do a lot of work because you have to identify the potential at least like 5 or 6 different points around the particle and then connect those particles to get that lines. Okay, now those lines are actually the potential lines technically. Okay, what I talking earlier here in my drawing here. Any question? Everybody get that idea? And then you can see now if I go into here, if I do the same concept, you can see how the shape is changes. Around here, close to the plate, it's look like more elongated one side. You can see it look like an ellipse, right? You go all the way towards here, ellipse getting much bigger, bigger and bigger. And then if I cross a certain point, you will see ellipse getting very different shape and then you start bending towards the point particle. Let me make it smaller. You see that? Now you can see around the point particle, it's again become a circular. So that line is actually the equipotential line. Okay, it's very different. The reason, depending on the shape of the charges, what that line tells you, if you go anywhere on that line, potential should be the same. So that's the idea. Okay. Any question? Okay, let's do then couple of measurement for this one too. Okay, like we done earlier. So let's go back again to the close to the positive electrode and then let's measure 5 different measurements. Okay, starting from 10 centimeter line. Starting from 10 centimeter line, first one is maybe like 289.6. Voltage 289.6 and 10 centimeters. We can do the electric field at the end. Okay, let's do the measurement first. 20 centimeter line, maybe 214.0. And that is 20 centimeters, 0.2. I need at least 1 decimal place here and maybe 1 more decimal place for this one. Okay. And next data point, let's take a look. That should be around 176.7, about 30 centimeters. This is our last data set. It's going to be done after this, 150.8 and about 40 centimeters, right? Then let's do one more data point, 129.7. 129.7, about 50 centimeters. Now electric field value is still should do the same, right? So electric field value should rapidly starting to decrease the magnitude going towards there. Let's take a look. So the ratio between these two cells and then click and drag. So that does, so it's about the same numbers as earlier. By changing the electrode negative into like point like doesn't change much, but you can see electric field value is actually decreasing rapidly, okay? So we cannot estimate the charge by using that electrode because we can use only point like particles to do that. And this picture we can save by including everything. We'll include all the equipotential lines and all the it's going to be look like it has all the electric field lines, equipotential lines, and the sensor, and then all the other information, right? So let's take a picture of that one to here. That's going to be our last work. Then we will talk about last few questions. Then we're done. So let's take a picture of this one.
So how do you draw the lines?
Yeah, all you have to do if you want to get the equipotential anywhere, just bring this sensor into any place, click on this pencil icon. That will draw the line automatically. Okay.
Okay, thank you.
Yeah. So that's why if you take in doing this in-person setting, drawing that lines, equipotential line going to take a lot of time. It's like almost half the class or even more. Sometimes we can't do any calculation because that drawing itself, because we have to do like 3 different drawing for this one itself. That drawing going to take a lot of time, almost like close to 1 hour, 1.5 hours or so. So that's it. Then we'll rename this one also, this picture. Maybe it's a different type of electrode one side, right? This should be then figure 3. This should be electric map for the plate-like and point-like electrode. Plate-like and point-like electrodes. Okay. So I think then we done all the calculation and everything. 3 tables, and the last last table is not a data table or anything. It's just asking a little bit of question, extra question. Those questions are from your lab manual. Very end lab manual has this question. Let's go through those things, then we can stop from there. Okay. So the question 1 asking, is it possible for 2 different equipotential lines to cross each other? Explain why or why not. Then to answer that one, best way is that now you have equipotential line, you can take a look whether equipotential lines are crossing each other or not. Okay. If it is not crossing each other, then you can explain why or why not, depending on the background information which we discuss. Okay. Just write it down, maybe 1 or 2 sentences. You don't need to write it down the whole paragraph. So that's why this last figure is important. Okay. So make sure you actually visualize the equipotential lines, then you can get a better idea about what this question is asking. And the question 2, is it possible 2 different electric field lines to cross each other or not? That also you can easily get the idea by looking at the map. Do you see anywhere electric field lines crossing or not? If not, then why? Just explain by 1 or 2 sentences. That's good enough. Write it down the answers just in front right here. And where do the electric field lines begin and end? If they are equally spaced, at their beginning? Are they
Yes,
equally
Professor.
spaced at the end? Yeah, go ahead.
Wait, so what'd you name figure 3?
Figure 3, we name as electric field map of plate-like and the point-like part, point-like electrode.
And
Okay.
what were your numbers for the voltage, like for the last graph, for the last table?
Last one, voltages, I measured each 10 centimeter, about like 289, 214, 176, 150, and 129.
176. Okay. All right, thank you.
Okay, then let's take a look the next question. Where do the electric field lines begin and end? That you know by definition. Electric field line must start at positive, must end at negative. Then the next part, you have to take a look your first diagram. Okay, take a look the first diagram, then you can first or second diagram, then you can get a better idea. If electric field line equally spaced beginning of right here in positive side, is it the same spacing on the other side? Okay, that's what it's asking. That depending on amount of charge on the plates. If the charges are same, because number of charge decide the density of the electric field lines. Okay, if the number of charges are same here on the positive and negative, then the density, how many lines per given area, should be exactly the same. Okay. So explain that in 1 or 2 sentences. You don't need to write too many, okay? 2 sentences, 3 sentences is enough for each answer. Let's take a look then. 4, if you want to push a charge along one of the electric field lines from one conductor to the other, how does the choice of electric field line affect the amount of work required? So if you're pushing and that's very simple, like the work done, right? If you moving something from one point to another, if you move to very closest space or the closest distance, your amount of work done going to be very less if the electric field strength is the same. If your electric field strength is the same, but if you're moving further longer distances, your work done going to be different. But take a look the field map to get a little bit of idea, then write it down. Okay. Then question 5, potential is everywhere the same on the equipotential line. Is the electric field everywhere the same on the electric field lines? If that is the case, we know equipotential mean potential is same, we know. These black lines right here represent that. But is the electric field strength same if you go from electric field line from positive to negative? That answer you can easily answer by looking at our first calculation. You don't need anything. Actually, technically, you have all the others too, whether the electric field behave the same or not. You have the data right here, okay? Whether it's the same or not, observe the data and then write it down 1 or 2 sentences. If not, you know why, because electric field value is actually inversely proportional to R. Okay, you go further away from the charge, electric field value changes. What else? Then it asking how much work has to be done in order to move an electric charge along the equipotential line. That's a good question. What do you think? If you move a charge along equipotential line, how much work has to be done? We discussed answer in a different manner earlier. So one of you asked that 0 point, why the potential is 0, then we talk about a reason for that. If you bring a charge particle from distance to that point, then if I have a positive and negative side, negative charge particle, then I do positive work done, negative work done cancels out, then that middle point I can find a 0 point. Equipotential means the potential level are same, so which means the work done happens only if you're moving between different potential values, okay? So that's the energy technically, right? If you have 2 different energy points, you have to do a work done. But if you don't have 2 energy points, if you move in the same energy line, then you don't need to do any work done. Like, for example, think about physics 1 point of view. So if you go into the physics 1 point of view, the potential energy you discussed there, right? So potential energy, this is relative to the ground. Ground point is the potential energy 0. If you're moving the object from here to here, this word direction A to B, there's no potential energy change. Delta potential energy is 0. But if you move object from here to there, different place C, then potential energy A is actually 0, but C, you have a potential energy mgh. Then you have to do a work done, okay? There's say exact same concept here, but we're talking about now electric potential, okay? That's the difference. So which means if you are moving an particle along the same equipotential line, then there's no energy difference at all. Then the last one, where do the equipotential line begins and end, then you need to take a look whether does equipotential line has the beginning and end. That's the real question, really, right? It's not where does it has the beginning and end. Can it have the beginning and end? Because electric field line particularly define per charge particle start from positive, go to negative. But is there a definition like that for equipotential line? Is there a beginning point and end? Of course. If not, then there's no way to tell where it should begin or end. Then write it down, answers along with that, okay? So I gave you a little bit of hint for every answer. I think that should be enough to write it down, couple of sentences first for that. So I think we can stop from there. But if you have any question, I know one student earlier was asking some information who joined the class this week. You can stay. I can talk to you what we do last week and then how we did and everything. For everyone else, we'll stop here officially. I will see you guys next week then. Okay, upload data sheet for this one by tomorrow midnight. There's no lab report, only data sheet for this lab also. Okay.
Thank you, Mike.
Professor, I just have one quick question before I go. With last week's data sheet, for some reason, when I try to upload it, it wouldn't show it on Blackboard. However, when I went to go download and look at the data sheet again, it showed none of my calculations. I just sent you an email of what I have from my Excel sheet.
Can
Just to
you
let you know.
re-upload that?
I'm sorry?
Can you re-upload that to the Blackboard?
I could give it a try. I haven't tried it, but
make sure that's do you use in the Excel in your computer or online version?
Microsoft Excel from the computer, yeah.
Computer, right? Then it should be fine. Make sure it's that extension is Excel SX, something like that.
Okay, I'm gonna try and resubmit it on Blackboard, but
Okay.
I sent you an email just so.
Okay,
Just
check it
explain.
out. If it's impossible, then you can email me that as attachment. Okay.
Okay, thank you so much. Have a good night.
Mhm.
Professor,
Yeah.
I just have a question with something on my table. I'm getting the exact same numbers and I have like a different formula.
That may be definitely if it is a calculated value, definitely because of that. I can stop sharing. You can share your side. We can take a look.
Yeah, I'll share my screen.